All right, we are ready to talk about the 6 phase changes. How a piece of matter, for example, goes from a solid into a liquid, which I know you know is called melting. But there are other phase changes as well that we're going to define and discuss throughout our set of notes today. Notes 2D, the 6 phase changes. Ready! First, though, we have to understand something. A phase change is a physical change. All physical and even chemical changes, though, follow what you see on the screen there, called the law of conservation of matter, which basically says this: matter cannot be created or destroyed, but only change from one form to another. For example, regardless of what we do to a piece of matter, we have exactly the same number of atoms that we started with and end up with. Whether we just tear a piece of paper or we burn the piece of paper. Tearing is just a physical change. Burning would be a chemical change. But all the atoms that made up that original piece of paper are still there, just rearranged and possibly recombined. All matter follows a law of conservation. We'll see other laws of conservation as well, such as a law of conservation of energy, law of conservation of work and momentum, and so on, a few more as well, that we'll talk about at other times. In short form, the total amount of matter before the change occurs is equal to the total amount of matter after the change occurs. All atoms are present and accounted for both before and after the change. Ready? Phase changes, remember, are physical changes only. So let's say, for example, I take a piece of ice out of the cup and just set the ice on the table. The ice begins in the solid phase. As heat energy from the room and the table enter that ice cube, then the molecules will eventually start to gain more energy and move around a little bit. By spreading out, the solid ice is going through the melting phase. And after all the molecules of water, H2O, gain enough energy, they will all separate and we'll have liquid water on the table. Notice, though, the phase change is called melting, going from solid to liquid. Now, once all the ice is melted, then the liquid water on the table will start absorbing some of the energy from the room. This may take a while depending on how much water is on the table, and you'll begin the process of vaporization, which is changing from a liquid to a gas. Vaporization is the term that means liquid turns into gas. Evaporation means the molecules will take their own sweet time going from the liquid phase into the gas phase. Boiling is simply a process that will add a lot more energy a lot faster and cause vaporization to happen much faster. We then end up in the gas phase where the molecules are much further apart from each other and moving at higher speeds. But remember, all 6 phase changes are only physical changes. Whether we have H2O as a solid, a liquid, or a gas, we still have H2O. That water would not have changed into any other substance. In all phase changes, the substance remains the same kind of matter. It takes heat and temperature to change the amount of energy that the particles contain. When we add heat, molecules start to move around, spread apart. When we reduce heat, such as using a refrigerator or a freezer, then those particles lose energy and come closer together. Remember, we talked about the characteristics of solids, liquids, and gases last time. Ready? In melting, you see the picture of the ice cubes sitting on the table. The melting process will begin almost immediately by putting that ice onto the table. Even in a cool room, the temperature of the air is warmer than the temperature of the ice cube. Same with the table. So the ice is going to absorb energy from the table and the room around and start the process of melting. This is solid to liquid, is the definition of melting. Ice melts at 0 degrees Celsius, which is equivalent to 32 degrees Fahrenheit. When ice, which is cooler than 0 Celsius or 32 Fahrenheit, starts to absorb more energy, once those particles get a temperature above 0 Celsius or 32 Fahrenheit, those particles will begin to separate from each other. This happens by adding energy, adding heat energy or thermal energy. Molecules begin to spread out. You see on the screen the picture of the ice turning into liquid water because of adding this energy from the table. Now, every substance has its own melting point. Water is the only substance that will melt at 0 degrees Celsius or 32 degrees Fahrenheit. Nothing else has the exact same melting and freezing point. Now, other substances may come close to those temperatures, but they won't be exactly the same. Ready? In freezing, same picture. Let's say we want to turn the liquid back into a solid. Fill up the ice cube tray, put that ice cube tray in the freezer. The refrigerator and the freezer remove energy from whatever we put inside. The liquid, once that liquid loses enough energy to reduce its temperature to the correct point, then freezing will begin to occur. So again, for water, H2O, that's the same as the melting point, 0 degrees Celsius, 32 degrees Fahrenheit. Freezing and melting points are exactly the same temperature for the same substance. Water freezes and melts at 0 degrees Celsius. Now I said the Fahrenheit, but I'll go ahead and write it up there just to give you the comparison there. 0 degrees is on the metric scale called Celsius. 32 degrees for the melting and freezing point is on the temperature scale in the English system called Fahrenheit. And there's also a Kelvin scale that we'll talk about another time. For example, molten iron, which makes up the center of the earth, iron and nickel, but molten iron freezes at 1,500 degrees Celsius. Now, we tend to think of the word freezing as feeling very cold to us, but freezing is just the name of the process of a solid turning, or a liquid turning into a solid, maybe at very, very high temperatures, as you see here. For iron, 1,500 degrees Celsius, that's equivalent to 2,732 degrees Fahrenheit. 1,500 times 1.8 and then add 32. That's how you change Celsius into Fahrenheit. Multiply by 1.8 and then add 32. Ready? Vaporization is the process of a liquid turning into a gas. This happens when the liquid particles gain even more energy and allow the particles to separate even further. Some of the molecules move faster and escape. So if we took our cup of water and just set that out on the table, depending on the size of the cup, the width of the mouth of the cup, and how much water we put into the cup, that may take weeks or even months to fully evaporate. If we just have a very small amount of water, a few drops on the table, may not take very long at all. Evaporation is a very slow process. Let's stick with water because that is something we can all consider and think about very easily. The molecules at the top of the surface kind of look around. Oh, nobody's watching. I'm going to jump right off into the air. And then a few more molecules look around. Hey, nobody's watching. We're going to escape too. And over time, it may be a long time, eventually all those molecules are going to leave the cup and go into the air around that cup. Boiling, I said a moment ago, boiling is a process that we do to add a lot more heat in a short amount of time, speed up vaporization. For water, that's 100 degrees Celsius or 212 degrees Fahrenheit. In science, though, we typically use the Celsius scale because that's metric. And again, boiling is just making vaporization happen much faster. So you put the pot of water on the stove, turn the burner up to high. Eventually, you'll see the boiling happening. Those molecules of water are gaining more and more energy much faster than just letting the water sit. And you might start seeing the bubbles form and then the gas escape into the air, and you'll see the steam as well. Ready? Condensation is a process of a gas turning into a liquid. I'm sure you've seen, you go to the restaurant, you order a cold drink, cold water, ice water, or cold soda with ice, and after just a fairly short amount of time, water is on the outside of that glass. Where did that water come from? The process is called condensation. The water vapor molecules surrounding the glass, some collide with the glass, and because of the ice inside, the ice starts to absorb that energy. Well, those water vapor molecules touching the glass come closer and closer together, close enough eventually to where we will see the liquid water on the outside of the glass. Lower heat energy, so the molecules start to come closer together. Particle motion slows down as well. And before long, we have enough molecules close enough together that we can now see the water on the outside of the glass. The water itself on the outside of the glass is not called condensation. It is called water. Condensation is a process that let that water get there. Another good, fine example, go outside and the grass is wet. Early in the morning, didn't rain last night, we didn't use the sprinklers, but the grass is wet. Same process of condensation has occurred. The water vapor touches the grass blades, cools down, and the particles get closer together into liquid form. And we talked about the outside of the cold glass as well. But the process of a gas moving into a liquid is called condensation. Ready? Sublimation. Think of dry ice. Skipping the liquid phase. Dry ice is in solid form. It's not ice, it's frozen carbon dioxide. If I put a piece of that onto the table, we would not see liquid carbon dioxide. We would immediately see gas because those carbon dioxide molecules gained enough energy fast enough to completely skip liquid phase and turn into a gas. So sublimation is when a solid becomes a gas. Dry ice, we just talked about. Mothballs. Those are solids that will become gas. Put a little drop of water on a mothball and you may be able to see the vapor come up. Of course, mothballs can be poisonous. Deposition is when the liquid phase once again is skipped, but this is backwards than sublimation is. Deposition means the gas is becoming a solid. So the gas particles lose enough energy fast enough to skip the liquid phase and go immediately into the solid. Frost on the objects outside during the winter. I go outside, get ready to drive to school. There's ice on my windows. Water vapor in the atmosphere touches the glass, and because it's winter and it's much colder, those particles lose their energy much faster, and I get teeny tiny little bits of ice on the window. Teeny tiny little bits of ice we call frost, and sometimes I have to let the windshield wipers run for a couple of minutes to try to generate friction that will gain enough heat to melt that ice, and then I can use the wipers to clean off the window. Didn't mean to hit that just yet, but going from gas to solid, skipping the liquid phase, that is called deposition. Ready? And we're almost done. Look at the picture. Maybe a little bit fuzzy, but we're going to focus on this yellow point right here. The white says ice, the blue says water, and the pink says steam. So this is all H2O, dihydrogen monoxide. And you notice that this one particular spot right here, color that in, maybe you can see it better. This is where H2O is existing as all three of the phases of matter in the Earth's atmosphere. Solid ice, liquid water, and vapor steam. Again, all are H2O. At this point right here, as you see in the middle there, 0.01 degrees, so 1/100th of a degree Celsius and 32.2 degrees Fahrenheit, water can exist naturally at the same time, at the same temperature as ice, water, and steam. Solid, liquid, and gas. Okay, so now we'll put up the definition of triple point and we will be done. Triple point is the temperature and pressure at which a substance exists as a solid, a liquid, and a gas equally and naturally without being forced to. And there you see again, triple point of water, 0.01 degrees Celsius, and 32.2 degrees Fahrenheit. And that is going to do it for the 6 phase changes. Don't phase on me. Thank you.